Okay, open the whiteboard. So the question was prove that 1 plus c, where's this whiteboard? Yeah, 1 plus c squared plus blah 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 blah. What's that? Cn is equal to 1 minus Cn plus 1 over 1 minus C. All right. So we checked, we already proved that it was true for n, because remember, we're using this as our P of n, that statement, that is equal to that. So we already showed it was true for 1. We put 1 on the left side. That just leaves, when I say 1 on the left side, I mean 1 in place at the end. So remember, it goes from 1. That's sometimes mistakes students make. They're not sure where to stop. The n is the power of the c. So if the c is 2, you'd stop at c squared. Beg pardon. If the n is 2, you stop at c squared. If the n is 3, you stop at c cubed. But since the n is 1, it will be just 1 plus c on the left. Matter of fact, since I'm just going to persons aren't here, let me just do it. So for n equals 1.
Sir, morning. Sir, you're starting before the 5 minutes, sir.
Ask the students if I started before 5 minutes. Ask them. I started right away.
Right, sir. So this is the first thing?
Yeah, I'm just going through the thing last class. The last
Okay,
thing we did in last class.
Okay, sir.
So you haven't missed anything because I know you understand the first part when n is 1.
Okay, sir.
All right, so for when n is 1 now, we put it in. Matter of fact, let me write the 1. It's right here in the power for the c. On the right side, we're going to have 1 minus c to the 1 plus 1 over 1 minus c. Oops, c. That's a c right there. All right, so on the left side, we have 1 plus c, nothing changed. On the right side, we're going to do some factoring. So that's 1 minus c squared, the difference 2 squares. We're going to, let me just make sure you see that it's 1 minus c squared over 1 minus c. So since that's the difference of 2 squares, you can have 1 minus c, 1 plus c, which then breaks down to just simply 1 plus c on the left and 1 plus c on the right. So it is true for n equal 1. See, let me underline where I'm saying n equal 1. Here, here, and here. Replace all the n's with 1. All right, so when n is 1, we see that both the left and the right side are true. So this is the second method I showed you last week. It's a method where you're adding stuff right up to the n. You have a method that just substitute values of n. But in this method, you're adding right up to the nth value. All right, so far we've shown that it's true for n equal 1. We're now going to check to see if it's true for n plus 1 after we assume that n is true. I mean, that it's true for n equal 1. Beg pardon. We're going to assume this is true for n and prove that it's true for n plus 1. As I said before, this method is useful because if you already show it's true for the first term, and then you assume it is true for the nth term, and prove it is true plus 1, that means it will be true for all of them. Because if it's true for the first, that could be the nth, the n plus 1 could be the second, then it's true for the second again, n plus 1 could be the third, so it's going to keep being true upward and upward all the way. So once it's true for the first term, and it proved that it's true for the n plus 1th, having assumed the nth term is true, it will be true for all terms. All right, so we're assuming that 1 we're assuming that the term that this statement we got is true. So 1 plus c squared right up to cn is the same as 1 minus cn plus 1. Make sure I remember the n plus 1 this time, over 1 minus c. So we're assuming that this statement is true. I'm going to write below it now what we want to prove is true. We want to prove that this is true. 1 plus c squared plus right up to cn, then cn plus 1. We want this when it goes up to the n plus 1th term or power. It will now be equal to which is not true yet. We want to show that it's true. That is equal to 1 minus c. Replace the n with n plus 1. So that's going to be n plus 2. Because it's n plus 1 plus 1, which is n plus 2 over 1 minus c. So we want to show that that is true. How did I get that? You add one extra term. Because so far we have assumed that when it's true, we have been given the statement that from 1 plus c squared right up to cn is equal to 1 minus c to the n plus 1 over 1 minus c. So when we go up to the n plus 1th term now, you're going to increase, you're going to add one extra term to the left, and it should cause it to be equal to that thing on the right. Because whatever the power, if you look at this, if the final power is 5 on the left, so if it goes up to c5, then it should be 1 minus c6 over 1 minus c on the right side, because it's a plus 1. So if we're going up to the n plus 1 on the left, then we should go up to the n plus 2 on the right in the numerator. All right, so let me just mention something here. Whatever you assume to be true, we have assumed that this little box right here is true. Whatever you assume to be true, you have to use in your proof. You can't go prove it without using it, because it is your assumption that you must use to prove that the next statement is true, because you build on that assumption. If you can't use the assumption to prove that the n plus 1 is true, then you haven't applied the method of induction, the principle of induction, sorry. So, oh, you guys have this written already, so I don't have to wait for it to write, I think. Is anybody writing? No. All right. So I'm going to build on that second part. That bottom part right there, I'm going to use that circled part I'm going to use it in what we wrote below it. So I'm going to replace this part right here now. Let me underline it. I'm going to show you what I'm going to replace. I'm going to replace this portion right here with this thing that we have assumed that is equal to right here. As you can see, 1 plus c squared plus blah 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 right up to cn, c to the power of n. We have assumed that that is equal to 1 minus c to the n plus 1 over 1 minus c. So we're going to replace this underlined portion with that portion circled over there to try to get this thing on the right. All right. So here's what we're going to have now. 1 minus cn plus 1, 1 minus c. All right. 1 black ink. 1 minus c. I'm at you know what? Write it again so you can see exactly what I'm replacing. And there's no confusion. 1 plus c squared plus dot 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 plus cn plus cn plus 1 is equal to, we want to show that this as a question mark, 1 minus cn plus 1 plus 1. I'm actually writing it out this time. So you see where everything came from. We have replaced the n with n plus 1. That's how we get n plus 1 plus 1. All right, so we're going to replace on this left side now. I'm going to replace this with our assumption. And our assumption, right, in blue ink is 1 minus cn over, sorry, cn plus 1 over 1 minus c. That's what we underlined a while ago. That's what we replaced it with what we assumed before. And we still have that cn plus 1 term. And we want to show on the right side that is equal to, so it's not yet equal. Well, it's equal, but we don't know that. We have to prove it. And we want to get it to be equal to this thing on the right here. I want to show that it's the same thing. So we'll do some algebra. You know, when you're adding a whole number to a fraction, you just multiply by the denominator, add it to the numerator. So that cn plus 1 is multiplied by minus c. So cn plus 1 times 1 minus c all over the 1 minus c. Still not completely sure if it's equal yet. So we're still checking n plus 2, 1 minus c. All right, so on the left side, if you can see my writing, because some of these pluses look so weird. Anyway, so we're going to expand this. We get 1 plus, where did I get plus from? sorry, that was supposed to be minus. Oh boy. This is a minus, and this is also a minus. So squeeze it here, minus. I don't know where plus came from. Oh, the plus came from, I was thinking about the last part. So it is minus c to the n plus 1 plus, expand that bracket now, cn plus 1 times 1 is just cn plus 1. And c to the n plus 1 times the next c, let's add the powers, that's cn plus 2. All over 1 minus c. And we're getting close. As you can see, starting to look like it, because we have the cn plus 2 now. So some cancellations take place. Use the green ink. That one cancels this one right beside it. And we're left with 1 minus cn plus 2 all over 1 minus c, which is exactly what we have on the right. 1 minus c plus 2 over 1 minus c. So we have shown by induction that that statement is true for all n. What was the n again? Greater than or equal to 1? Or was it all n in natural numbers? What's the thing? So it's true for all n, as long as c is not the number 1. So, was that any better? Any clearer? Because the last class I made a mistake with the n. I didn't put it into the last part, so
Sir,
confused me.
if I didn't know who you were, I would have thought that the person that taught us this the last time is somebody different. This makes perfect sense now.
No, but I tell you the last, because of that mistake I made with n plus 1, you probably confused everybody. It wasn't flowing. And I went a bit slower this time.
Thank you, sir. This makes perfect sense now.
All right. Or maybe I was rushing too because it was close to the end of the class. Yes, that's true. I think it's like went over time too. Maybe that was the reason. Well, I'm glad that you guys understand now. So you see the same thing, I didn't write anything different, I wrote the exact same thing as last time. It was just because maybe I was rushing. All right, so I'm assuming you guys didn't write it again. Did you? Is anyone writing? No. All right. So let's do another one to make sure that you understand everything. Let's find one here. Boy, I'm looking at my computer, but I should have my textbook, you know. Let me find one. It's sweet, Laffer. You go on here, Laffer, laughing at me. Where is this? I thought it says right here. Aha, here we go. Prove by induction that I want one like this. Now with the substitution for the n. This here's one. All right, let's do that one. So it says prove. Let me write it here. Prove that 1 cube plus 2 cube. So this is sum of cubes plus 3 cube plus dot dot dot. You know, sound nicer one than this. Plus n cube is equal to n times n plus 1 over 2 squared. All right, that's it. So we're going to prove by induction that, for all n is, for all natural numbers, for all n in natural number group of numbers, that's an n at the end, capital N. So you're going to only use 1, 2, 3, 4, 5. Oh, I remember the one that I was going to use. I'm going to show you guys after this. It's a nice one. It needs a little more reasoning because you have to, well, you'll figure it out. All right. So, so let's start with, so we're calling this our P of n. That is our P of n. Can't write it again, so I must squeeze in the P of n right here. So this is our statement for P of n. So when n is 1, P of 1 tells us that the left side, what would be on the left side when n is 1? Hello? Like a trick question. What would be on the left side when n is 1? Wait, are you guys hearing me?
Sir, n into
Remember
the
we're
1.
using, no, not quite. We're using P of 1, you know, so we're replacing n with 1. Look at the nth term. Well, 1, yes, Lafern, but you know, write the whole thing. 1 to what power?
1 to the third.
Right, good, 1 to the third, because if you look here, you know, these numbers represent n. 1 here, 2 here, 3. If you want to know which one it is, look at the last one that has the n. So it starts from 1 cube, that's the 1 for the n, then 2 cube, 3 cube, right up to whatever n is cubed. So if n is 5, it will be 1 cube, 2 cube, 3 cube, 4 cube, 5 cube. If n is 2, it will be 1 cube plus 2 cube. If n is 1, it's just 1 cube. And because natural numbers start from 1, as Michaela said, it has to start at 1 right here. But remember, Michaela, the 1 was not in the power, it was in the base. So if it was something right up to something to the n, then 1 would have been the power. But in this case, the 1 is in the base, so it's just 1 cube on the left side. Uh-oh, wrong ink. Oh, whatever the matter. 1 cube. On the right side now, we're not sure if it's equal yet, so put a little question mark there. We're going to replace all the n's with 1. So it's going to be 1 times 1 plus 1 over 2 all squared. So I want to see if that is, if those are equal. On the left, we just have 1 cube 1. On the right, we have, at the top, we have, what's that, 1 times 2, so that's just 2 over 2. And it's squared. So obviously we can see that left side is equal to right side. So it is true for n equal 1. So this is something that you must always get right, you know, because all you have to do is put in the first number. The question will always tell you which number to start at. It can say n is a natural number, it can say n is a real number, it can say n is a we don't want the real number, because with real numbers you can't start anywhere. But it will tell like it's a positive number, it's non-negative. By the way, if it's non-negative, where will it start? What will be the first non-negative number? 0. 0 backslash or 0 front slash? I know it means 0. Just dropping it. Typo. All right, so 0. So based on the question, you will figure out where to start. Sometimes this is, well, I don't want to tell everything. Let's see if you can figure it out later. All right, so take that off. Is anyone still writing this first part here? I'm going to erase it and then start with the true for n equal. Assume p of n and go for it. Anyone still writing? No? All right. So we're going to assume that it's true for p of n, which is the statement that we started with. Here's back to black. So we're going to have 1 cube plus 2 cube. The same statement we had before. We're going to assume it's true. So we're assuming that everything right here is a true statement. Oh Lord, I missed the n. Put on the next slide. Over 2. And we want to show that it's true for p of n plus 1. So for the p of n plus 1, we're going to have 1 cube. We're going to go right up to the n plus 1 term. So it is 3 cube. Why did I put 3? Dot, 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 dot. N cube plus n plus 1 cube. Hope you guys remember your college algebra. Pascal's triangle. So we have on the right side, we should have the n plus 1 term. Follow me carefully now. On the right side, I'm going to replace all the n's with n plus 1. That's what we want to get. So we should n plus 1 plus 1 more, which is just n plus 2. On the outside, we're going to replace that n outside the bracket at the top. We're going to replace that n with n plus 1 as well. So let's make sure you understand that. The two n's in the numerator, I'm replacing both of them. The one inside the inner brackets, we have n plus 1. We're going to replace that n plus 1. Sorry, we're going to replace that n with plus 1. So that gives us n plus 1 plus 1, which is n plus 2. The one on the outside replaced as well. Make sure you put the brackets multiplying it, If you just write it as n plus 2 close bracket times n plus 1 without the brackets, you just be multiplying the n and not the entire n plus 1. So replace both of those n's to give us that numerator. And we still have a 2 down here. If you have 2, we still have the square on the outside. We don't have to run that. You can if you want. So you can better see what's happening on the right side. But if you look at it in your head, you can see it's going to be n squared plus 3n plus 2. But if not, you can factor further and you see it. All right, on the left side now, back to the left side, we're going to replace all of this with what we assumed up here. As you can see in the line above, 1 plus 2 plus 3, all cubes, right up to n is going to be replaced by what is on the right, n plus 1 times n over 2. So I'm going to replace all of that with, put in a different color ink, n plus 1 times n over 2 and it's squared. We still have that additional n plus 1 cube right here. All we do is replace the part that's on the line. And on the right, we still have the same thing as over there. Matter of fact, I'm going to write it. That same thing. I'm going to write it when I get to it. So now we're going to expand on the left side to see if we can get it to look like what we have on the right. We'll take our time now. So you can see so far the denominator is actually 4 when you square it out. So I'm going to have a long line right here. All right. All right. You see in the brackets there, it's n squared plus 1. Sorry. When you expand the bracket at the numerator, plus the part in blue, it's going to be n squared plus n. So because I don't have such a good, I don't have a big whiteboard here, I'm just going to ask to work with me. I'm going to square, or maybe I'll write it, n squared. A little extra writing won't kill me. That top part is this. I squared it out yet. Remember, it's over 4. But I'm doing 2 steps in 1. I'm going to add that same, this n plus 1 cube to the fraction here. I'm going to put it in the numerator from right now. It's going to be 4 times n plus 1 cube. Let me know if there are any questions about that. Everybody understand what I did a while ago? Or anybody didn't understand? Okay, good. And it's still equal to the right side over here. All right. So now I'm going to expand that numerator. So remember, it's a square. So just to expand in the square, square the first term. So that's n to the 4. Multiply both of them and double it. So that's n times n squared, which is n cubed times 2. I'm going to have that twice. And oh, that's a 3. Look like that. Yeah. And we'll square the last term, which is n squared. Plus, if I'm not going to expand. Do I have to expand it? I might have to expand it. Let me expand it. So we're going to have 4n. Oh, by the way, you know what? You guys tell me this. I'm going to expand that n plus 1 cube. Tell me the terms that go in it. I start the first one. N cube. What comes next?
3n squared plus
Then
3n.
plus
3n.
okay. All right. You know it, man. So, all right. Well done. Well done. From here, you say the 3n squared, 3n. You must get the 1 right. All right. So this is all over 4. And it's still equal to the same right side here. I'm squeezing the last part at the bottom now. So I'm going to put all the like terms together. So we have n to the 4. That's only 1 time. Then we have a 2n cube and a 4n cube. So a 6n cube. We have an n squared and a 12n squared, so that's 13n squared. What is next? Where is this thing? 12n and then 4 all over 4. All right, so we're still not sure about the equal yet. The question mark was in the wrong place. It should be a tilde. The question mark should be right here. Question mark should be right here. So everything on the right hasn't changed. The right side is still the same. All right, so right quickly, and then we'll finish it.
Sir, just to let you know that I have a doctor's appointment for 12:30, so I'll be leaving the class at 12, and fortunately I'm going to miss the other class. I was trying to get the I was trying to get the doctor appointment to move to another day, like tomorrow afternoon will be better for me, but they said if I don't come today, I won't get back another date until sometime in October, based on the whole COVID thing. So,
All right, I understand.
yeah, so just to let you know, sir.
I'll try to put detail in the recording so you don't miss anything.
Thank you, I appreciate it, sir.
All right. You still writing, by the way?
No, sir.
All right. After Nikita finished?
Yes,
Right,
sir.
seem to be okay. I just realized something, you know. If you look back at this problem up here, look back right here. From right here, the thing I'm surrounding with green or highlighting here. I just saw easier method of doing it the hard way. Let me go back to that one here. I know you write that already, but to go show you the proof from that one at the bottom, I don't think you guys are good at the quadratics business. So. And even if you're good with it, it's still going to be harder. Go back to that first part up there. So we have the n plus 1 squared over 2n plus 1 cube. All right. See if I can remember that. Hopefully I remember it. But you guys have written notes, so you can tell me if I make a mistake. n plus 1 all over 2 squared plus n plus 1 cube. On the right side, we should n plus 1 times n plus 2 over 2 squared. Is that right? Especially the right side. I think the left side is right. Is the right side okay?
Yes, sir.
Oh, thank God. All right. So what I should have done, I'm going to square that left side still. I'm going to do it a little bit slower because I see how we can go much faster, so I don't have to rush it. It's going to be n squared because of the square, n squared, n plus 1 is squared as well. And this is n plus 1 cubed still. Over 4 now. So I'm going to add the terms. That's nothing changed over the left side, right side. I'm going to add the terms now. So you're going to have n squared, everything looking so ugly, man. N squared plus, oh Lord, it's not plus. I was writing a bracket. All right, leave it alone. N squared, n plus 1 squared. Adding that term now is going to be 4 times that. N plus 1 cube. All over 4. Now, on the left side, you can see that both terms in the numerator have n plus 1 squared. There's a n squared times n plus 1 squared, and there's a n plus 1 cube, which has 2n plus 1 squared. I'm going to factor the n plus 1 squared. Just make sure you guys understand. I'm going to ask you, what is left in the bracket? If I factor out n plus 1 squared from both of them, what's left?
N
Hello?
squared plus 4 and
Continue.
n plus 1.
Correct. Well done. But once you can see it, I don't have to explain it. Thank God. Well, as long as everybody can see it. So that leaves n plus 1 squared. I shouldn't do this in so many steps, you know. Should I skip that second step? No, we're not a page. We're going to have n squared plus 4n plus 4. When you factor that right side, that right part, the terms in the right bracket, what you get? N squared plus 4n plus 4. What that breaks down to? Hello? What's n squared plus 4n plus 4 as a square?
Sir, that's a
Lord,
perfect square.
yes, it is.
N plus 2 squared.
N plus 2. All right, I always remember this, especially in these type of courses. You asked a very good question a while ago. Is it a perfect square? You see, whenever the middle term is a half of the let me say it the other way around. Whenever the term on the outside, what I mean by term on the outside, I don't like the way I'm saying it. Whenever the last term, what's wrong with this thing? Whenever the last term right here is a half of a middle term squared, it's a perfect square. So let's say the middle term is 6 and the last term is 9, perfect square. So n squared plus 6n plus 9 is going to be n plus 3 squared. Our next way to look at it is if half of the middle term is the same as the square root of the last term, or I should say coefficient, the numbers, if a half of the middle coefficient is the same as the square root of the last perfect square. That's a good way to remember it. So n plus 2 squared is the answer. I'm going to actually simplify it a little further before I write the right side, which is equal to n plus 1 times n plus 2 all squared over the 2. 2 is all squared as well, to the 4, which is actually exactly what was on the right side. So all of these, we're unsure if they were equal, we're unsure if they were equal, we're unsure if they were equal, we're sure now at the end. In this case, both sides are equal. So we have shown that when you add the n plus 1 term, the cube, you get the same thing that's on the right. So it is true all n in the natural number set.
Sir, from the third line, how do you arrive or you get the fourth line from the third line? Because I'm missing something. The n plus 1 all square, over bracket n square plus 4. What happened to the cube? How you treat the cube?
All right. You see in that cube, that 4n plus 1 cube, there
Yes,
are
sir.
3n plus 1s multiplying, 3 of them. You agree? It's n plus 1 times n plus 1 times n plus 1.
Yes, sir.
Good? We factored out
Yes,
2 of them outside here. Right on the outside, we took out 2 of them. So that's why only 1 is left. That's why it's only coming
oh,
n plus
so
1.
you expand that way, then do the factorization, and we
Right,
end up
factor
with
it out.
that.
Right.
Okay, sir.
Then what is missing from the first one too? The n squared doesn't have the n plus 1 squared beside it, the factor it out too.
The factor of the n plus 1 square also.
Right, from both of them.
Okay, all right. Thank you, sir. Let me write that down.
All right. I should say Michaela did it. So let me know when you finish writing. I'll show you the next one and then move on to functions. Or not, wait, I haven't showed you. Well, I don't think it's showed anymore. I was going to say I didn't show you anymore the replace the n with a number. There are two principles. This is the second principle. I'll show you the example for the second principle. I think I'm going to show you one example for the first principle though. The first principle is more tricky than the second one. Second one is just adding and then factoring. The first one is more tricky. Okay, a bit trickier, that's a word. More challenging.
Sir, I'm sure I get it correctly. So it's the n square, large bracket, n plus 1 bracket plus n plus 1 bracket, and that represents the n plus 1 square.
Well, now, which line are you reading?
Let me go again. I'm taking the n plus 1 square because you said you expand that also. And I'm asking you, when you expand it, is it n plus 1 bracket plus n plus 1 bracket? That's how you expand it?
By expanding mean factor?
No. All right. When I asked you what have you done with the cube,
Oh,
you
yeah.
said that
Hold on. Tell you what. You finished writing everything?
no, sir. I'm all right. Finish writing.
Write everything here, so I can just go back and I can write that line bigger, so I'm sure what is happening. Because
Okay.
I'm not sure what you're asking. Number 10. Yeah.
You can go ahead, sir.
All right. So you want us to move from the third line to the fourth, right? Do you mean?
Sorry. Yes, sir. The mic was muted. Yes, sir.
All right. So let me see if I can remember that now. That's n squared, n plus 1 squared, 4n plus 3. All right. See, if I forget it, you can read it to me. So I think it's n squared, n plus 1 squared, 4 times n plus 1 cube over 4. That's right?
Yes, sir.
All right, good. So look at this now. I'm not going to factor out anything yet. I'm going to write it a different way. I'm going to write it as n squared, n plus 1 squared, plus 4 n plus 1 times n plus 1 squared. So I kind of expanded the n plus 1 cube. So you can clearly see that I'm going to factor out this one and that one. So I'm going to take out n plus 1 squared. All that's left will be that n squared outside here, and that 4n plus 1 beside the next one. That's what I did. That's how we got that a while ago.
Okay, so let me write that off. Okay, sir.
All right. So write this next one. I'm giving the instructions. So next one I'm going to look at is prove, of course, by induction. Prove by induction that the sum of the first n odd integers, the sum of the first n, what is this? N odd integers Oh, no problem, Anthony. You can catch up. So prove by induction that the sum of the first n odd integers is n squared. Prove by induction that the sum of the first n odd integers is n squared. So what they mean is 1 plus 3, let's use 5 of them, 5, 7, 9 now. Since there are 5 odd integers, that should give us 5 squared. The first 5 odd integers. If it was 6 odd integers, it should be 6 squared and so forth. You can check it. 1 plus 3 plus 5, that's 9. 9 plus 9 is 18. 18 plus 7, you see that's 25. So when I say the first n, n can be anything. If you want to add the first 100 odd integers, then you should add up to 100 squared. So instead of trying to prove that each one of them keeps going up to n squared, we just want to prove it, that it works for all of them. Once you are proving something for all numbers, you don't have to check for the rest. All right. So what is our statement that we want to write? What is our P of n then? You can't actually write words if you use numbers and letters now. First, n odd integer, let me start off, will be 1 squared plus 3 squared plus 5 squared plus dot, dot, dot. What will be the nth one? That's right, Anthony. What will be the nth integer? How can I write that? Write this thing again. So think about it, guys. What would be, how would you write the nth odd integer? That's 1 squared. No, it's not 1 squared. God have mercy. Any ideas yet? What's the nth odd integer? Nobody? Nobody at all? I am disappointed. Not quite n plus 1, because let's say, how do you write the 3? If there are 3 integers, right? Then n plus 1 will be 4. There are 3 odd integers. No. Down to something, no. Lafern is very close. Lafern, look at it, look at the board. The first 3, the third one will be 2
That's 2
times 3.
minus 1.
Correct, minus 1. So it's 2n minus 1. So check it. The first number, if it's 1 integer, 2 times 1 minus 1, that's 1. If it's 2 odd integers, the second one is 2 times 2 minus 1, that's 4 minus 1, that's 3. If it's 5 integers, the fifth one would be, based on 2n minus 1, would be 9. Check it. 1 first, 3 second, 5 third, 7 fourth, 9 is the fifth. So 2n minus 1 is the nth odd integer. Okay, let's make sure everybody's clear on that, because when you get questions like this, if you can't figure it out on your own, you can't do the question at all.
Sir,
Again.
being that they asked you for 5, they didn't say 5 is
5?
the sum of the
They said
proof
first
the
n.
induction of this n. Okay, n term.
Yeah,
Okay,
if they said 5
continue.
would be easier, just work it out right away.
Continue,
What's
sir.
first n, right? So it's important that you be able to find out how to write it mathematically. So using the n, since I said first n, you need to write the nth odd integer in a specific way, and this is the way they can be written, 2n minus 1. Anyway, so let's check it for p of 1. For p of 1, we have 1 on the left side as the first integer. On the left side, I mean the right side, we have 1 cube squared, beg pardon. That does make the equal stay, 1 equal 1. So it's true for n equal 1. So n equal 1, true. All right. So we're going to assume that the statement up there is true. We're going to assume that p of n, which is 1 plus 3 plus 5 plus whatever. Oh boy. Since right there, to put the 5 plus dot 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 2n minus 1. We assume that it's equal to n squared. Assume that that is true. Assume. So we need to show now. This is the part I should ask, you know. You guys tell me what to write. We want to show for Pn plus 1. I'm going to write the left side. No. All right, I'll just do it. If it was in class, I'll let you tell me, but right now, it's more difficult to write on this board, so I'll just do it. 1 plus dot 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 plus 2n minus 1. What comes after that? What term are we going up to? Lafern had mentioned it before. No, you never mentioned that before, Lafern. Matter of fact, the answer is right above the one you just wrote. It's 2n plus 1. Because you're going to go up to the, this. You see that last one was the nth term. We're going up to the nth plus 1th term. Or sorry, n plus 1th. N plus 1? Yeah, whatever. N plus 1th term, which is 2n plus 1 minus 1. This is one term right here. This is the next term to itself. If you increase n by 1, you know, you're going up to the next number. So you're just going up to the, so if it was the 5th number, you'd go up to the 6th, which is 5 plus 1. And we want to show that that is equal to, on the right side, I'm going to replace the n with n plus 1. So that's what I want to show is true or equal. All right, so on the left side now we're going to have we're going to replace this thing here. 1 plus 3 plus 5 right up to 2n minus 1. What are we replacing that with? Let's see if you guys are following. What would that be replaced with?
N plus 1 all squared.
We have to prove that before we can use it. We have to use something that we've already shown or assumed.
N
What have we
squared.
assumed? N squared. See it on the top there? We have assumed that 1 plus 3 plus 5 right up to 2n minus 1 is equal to n squared. So use n squared. N squared. And we still have the 2n plus 1. Because when you expand that bracket, 2 times n, 2n, plus 2 minus 1 is just 1. Look how easy this is going to be. This one is actually easier than what we did before. As long as you know what the nth term is, 2n minus 1. Without even going any further, I can't work this out. You see that left side is n plus 1 times n plus 1. As I told you before, if the middle term is half, sorry, if the square root of the middle term, chatting foolishness, if half the middle term and the square root of the last term are the same, it's a perfect square. And that is the number that will be in the square, n plus 1. So n plus 1 squared is equal to n plus 1 squared. So p of n is, as you can see, it's equal, is true for all n. The question never say all n, but the first n odd integer. So yeah, for the first n. For all n, too, same thing. Because the statement was regarding all n. Any questions?
Sir, just explain how we arrive the what one, we have a 2 over bracket m plus 1 minus 1. That how you derive that term.
Oh, which term? Sorry.
The term where we had the n line that says p n plus 1.
Yeah.
We have the 2 over bracket m plus 1 close bracket minus 1. How did you?
Oh, how did I get that?
Yes, sir.
All right. You see, because we're doing the n plus 1 term, replace the n. We need to add an extra term. So the one we have above is for the first n terms. We're going to go up to the n plus 1th. So to figure out what that term is, you look at this right here. You look at trying to get my different color. Use the green. Use this term right here, the one I'm circling in green or highlighting there. You put the n plus 1 raised to that n. So look at that. You see I replace that n with n plus 1. That's how I got that term. You get it?
Sorry, sir. Repeat. Go again.
You put the n plus 1 into the term that has the n. So that 2n minus 1, you replace that n with n plus 1.
All right, fine. But why n plus 1?
Oh, because you see, when you assume that it's true for n, you must now prove that it's true for the next term, which is n plus 1. That's how induction works, you know.
Oh, fine. Sorry, I've seen it now. Okay. All right.
All right. Yeah, man. All right, so let me know when you finish writing.
You can continue, sir.
All right. Do you guys need to see one with the n, where you substitute the first principle?
Sir. Wait, sir. One other thing, sir. We're supposed to prove. Aren't we supposed to prove when you put in the? Oh, okay. All right. Continue. I've seen it.
I get it. Okay. Yeah, I was asking if you guys want to see one where you just replace the n rather than keep adding up to n plus 1. Are you okay with it? Meaning you want to see another first principle induction. So far we did one first principle, 2 the second principle. I'm asking if you want to see another first principle, or are you okay? If you're silent, that means you're okay. Let's continue. Show another. All right. Well, I'm here asking if you want me to see one, but while I'm here talking, I'm looking for one. I should be able to find one though. Oh, here's one. I think we did one similar to this in modern algebra. All right. So write this down. It says.
Sir, I'm going to run now. So thanks a lot.
Oh, you check the recording. Yeah,
Yes,
no problem.
recording. Thank you, sir.
All right. The question is prove. So write that down. Prove that. Write this on the board. Prove that n cube plus 5n, n cube plus 5n is divisible by 6 So prove that n cubed plus 5n is divisible by 6 for all n in the set of natural numbers. For all n in n. All right. So think about this now. You write mathematically. Like what would be your statement for P of n? What's a way to say that that term right there is divisible by 6? Let me give you a hint. Think of it as multiple. Oh, that's not too big. Well, whatever, as long as you get it. So how can you write using this statement on the board, or that expression there? How can you write using that expression that is divisible by 6? In other words, make it equal to something.
N cubed plus 5n equals 6n.
You're correct, but you shouldn't use n again. Use a different letter. But you're right. So she's saying it's equal to. Oh, and are you guys hearing me? Hello?
Sir.
Oh, okay. I've seen that a while ago. All right. I just saw everything start like some circles going around everything like I'm disconnected. But anyway. All right. So she was right. She said let n cubed plus 5n be equal to 6 times a number. All right. Let me write something. So let's say we are going to use this. N cubed plus 5n is equal to say 6k. That k would be an element of what? For it to be divisible. For this statement to be divisible, that k must be an element of what set of numbers? Anybody? Anybody at all? Hello? There are only 5 sets to choose from, you know. No, not natural. But it's close to natural. It's very similar to natural. Let me give you a hint. So this, you can say yes or no quickly. No, it's a whole number, is it?
Oh.
I think I heard it a while ago. Somebody say something? Yes,
Sir.
integers. Correct, I heard you, but you were very faint, so I wasn't sure what I was hearing. But I heard the second time. Integers. Because let's check it. You see, if you use natural numbers, then it means that the number has to be positive to be divisible by 6. And that's not necessarily the case because negative 18 is also divisible by 6. But when you divide 6 by 18, sorry, 18 by 6, you're getting negative 3, not a positive number. So you have to ensure, in other words, negative 18 is equal to 6 times negative 3. And it is divisible by negative 6. It's divisible by 6, beg pardon. So you have to ensure that it includes the negative numbers as well. All right. So our statement that we want to prove, based on what I just gave you a while ago, is that P of n, we want to show that n cubed plus 5n, there you go, yes, is equal to 6k. Of course, you need to mention that k is a integer. That's a z. I don't know why it look like that. All right. So let's see if it's true for n equal 1. So for n equal 1, so this is in the first principle. We'll just replace the number. We get 1 cubed plus 5 times 1. Check if it's equal to the left. I mean the right. So as you can see, 1 plus 5 is 6, and 6 is equal to 6. So it's true for n equal 1. Easy peasy. The first part is always simple, and be careful. If you check the first part and it doesn't work, stop. Don't try going further. You won't be able to prove anything. Or you might even be able to prove a little thing, but it won't be true for all of them. So don't kill yourself going any further. That's the easiest question you can get where it's not true. And I might give you one like that too. All right. So we have shown that it is true for n equal 1. What would you do next? Since you started doing everything, what would you do next? Remember, it's a simple step that you know already. What would you do? Hello? Why is everyone so quiet? Wait, did I get disconnected again? Hello?
Sir,
Oh, yes. The A word.
assume
All right. Assume is
P
true
of
for
n.
n equal. All right. Assume P of n is true. Or as Anthony said, you can use K. Different courses they do it different ways. I'm just showing you the way they do it in real analysis. You could use the same K. If you guys do it the way I taught in modern algebra, it's the same thing. So if it confuses you to go use n, that's fine. You can use the K still. Not a problem. All right. What was I going to do? Yes, assume it's true for n equal for P of n. So that means that n 5n equal to 6k assumed to be true. All right, so we're now going to check for P of n plus 1 to see if we work out to get the right thing. Now, here's the trick, You see, for P of n plus 1, you don't have to do anything to the right side. All you need to show is that the left side is equal to sum 6 times k. So you don't have to worry about the right side now. All I want to show is that it's equal to a multiple of 6. So we're going to put n plus 1 cube plus 5 times n plus 1. And we need to find some way, oh Lord, there's no 1, 5 plus 1. Yeah, we need to find some way to show that that is equal to a multiple of 6 by using that initial statement there. The n cubed plus 5n is a multiple of 6. All right, so let's see if we can do that. So you guys know how to expand the using Pascal's. So that is n cubed plus 3n squared plus 3n plus 1 plus 5n plus 1. Oh, I should write that beside it, in the interest of space. But anyway, it doesn't matter. So far, you can see two things. Remember, we need to use this somewhere, You see this n cube and that 5n? 5n plus 5. Oh, thank you, Lafern. 5n plus 5. Thank you. It wouldn't have worked if I didn't have the 5, And then I wonder what is wrong. So 5n plus 5. So going back to what I was saying now, see, you see that n cube and that 5n, they appear right here. N cube, 5n. We're going to use them. Because remember, whatever you assume, you have to use it somewhere. So far we have n cubed, 5n, put them together. And we still have the 3n squared. We still have the 3n. And guess what? We have 6. 1 plus 5. So we have those right there. So remember, n is an integer. I mean, natural number. They say prove that it's true for all n in the natural number set. So we know that n must be 1, 2, 3, 4, whatever. Good. So far we have two multiples of 6. Where are they? We have this one, the n cube. We have the 5n. And we have the 6. All of them are there. All right, sorry. Yes, I was looking at something. So we have and we have 3n squared plus 3n plus 6 left. Wait a minute. That's hold on. Let me see if I should I 3n squared plus 3n plus 6. That would be n squared plus n plus 2. No, that can't work. All right. So we have the 3n squared and the 3n left. All right. So remember, you see this first part right here is already a multiple of 6. Why? Because we assume that n cubed plus 5n is a multiple of 6, or is divisible by 6, and we already know that 6 is divisible by 6. If you add 6 to any number that can be divided by 6, you can divide it by 6 again. So all we have to work on is that last part, that 3n squared and the 3n. So write that off, please, and then we continue. Or is anyone writing, by the way?
Yes, sir.
All right. Finish. All right. So remember, you know, we already know that the first part is divided by 6. So we're going to continue to that what do you call it? Last part here, the 3n squared plus 3n. So over here we have some multiple of 6. I'm right back first. N cubed plus, what was that again? I think it was 5n plus 6. And I think we had 3n squared plus 3n, if I'm not mistaken. All right. So as I was saying before, we already know that this left side, the n cubed plus 5n plus 6, is already a multiple of 6. So we're left now to show that 3n squared plus 3n is a multiple of 6. We need that to be a multiple of 6. So guys, how do you think we should approach this? There's a little trick to it. Let me give you a chance first to try it. What do you think we should do to get the rest of that, to show that the rest of that is a multiple of 6? It can be a little tricky, so I'll give you 2 seconds, well, 2 minutes to think about it. We have 8 minutes left. Any ideas on how we can show that that's a multiple of 6? Remember, this is a proof course now, so you're gonna have to do stuff, figuring out stuff like this. Minute and a half left. Equate to 6k. But if you do that, it's going to say it's equal to it. You can't just say it's equal to it without showing how you get it to be equal to it. Wait, question mark is there, yeah. All right, put it there. So how are you going to get to show now that it's equal to 6? See if there's common factors with n cubed plus 5n plus 6. All right, you can try that. Well, I know I thought of it that way. Check it out, let me know. That is an interesting approach. All right, this one might be a bit hard for you to figure out, but it has something to do with the 3 and consecutive integers. I think that's the most I can tell you. It has something to do with 3 and consecutive integers. All right, let me give you a hint. When you multiply two consecutive integers, which number can always divide it? Whenever you multiply two consecutive integers, which number is always divisible by? As I said, it's a bit tricky. I don't know if that's what I mean. 2, correct. 5 times 6 can divide by 2. 8 times 7 can divide by 2. 11 times 12, 101 times 102. One of them is always even, that's the point. So whenever you multiply two consecutive integers, it's always divisible by 2. So watch this trick now. As we said before, this first part right here, I'm going to write some stuff on the board before I go any further. But this first part we already say is divisible by 6. We assumed it already. And we know that 6 is divisible by 6. So we added a next term, went up to the next term to see if that's divisible by 6 as well. N plus 1. Well, watch this now. You see that 3n squared plus 3n? Remember, we know, Lafferin correctly said that n times n plus 1, if they are consecutive numbers, n times n plus 1 must be divisible by 2, because 1 must be even, 1 odd. So when your product is done, when you multiply two of them, because one of them must be even, it has to be divisible by 2. Look at this now. I'm going to factor this sum right here. I'm going to factor it to get use blue ink. 3n times n plus 1. And let me stop right there. You see where I'm going? Can you figure out where I'm going next? Oh, what's wrong with my throat? Any idea where I'm about to go? Anybody? I don't see it. All right. So Lafferin correctly said that n times n plus 1 must be divisible by 2. But at the same time, do you realize what's multiplying that? You know, so the important number right there to make it divisible by 6, the 3. So because n times n plus 1 must be divisible by 2, when you multiply that whole thing by 3, this entire product will be divisible by 6. Because if a number is divisible by 2 and you multiply the number by 3, then the end result must be divisible by 6, because 3 and 2 are in the multiplication. So, so this one you have to say a few words or whatever. But we would know that, okay, this divisible by 6 already in the assumption. This divisible by 6, and now 3 times n plus 1 must also be divisible by 6, because it has multiple of 2 and 3 in it. So whatever that number is, any two numbers multiplied must be divisible by 2, and because that result is multiplied by 3, it must also be divisible by 6. So it means that all three of them, we have shown the first one, the 6 of course is self-explanatory, and that last one, all of them must be divisible by 6, because of what I showed you with the last one. Here's the next way you could do it too. Probably show you next time, but there's 1 minute left. So, all right, tell you what, I might just write it and show it to you, because I can't go through this again next class. I'll just probably put it online. But you understand what I was saying about the 3 and the 2? Who is here? Lafern and Anthony. Wait, Michaela gone? Lafern say, oh, so she understands. You understand, Anthony? Okay, good. So in the next line, you'd write n cubed plus 5n. I can't bother write it because of time. N cubed plus 5n. Oh, you'd write it in the next line. You'd say n cubed plus 5n, ouch, is equal to 6k. 6 is equal to 6 times 1. And you'd mention that 3n, n plus 1 is equal to 3 times 2 times some k. Well, I should use k again. But anyway, since, and you give the reason I gave you a while ago, since it's a product of two consecutive numbers and 3, you mentioned that. Therefore, you write the entire line again. Dot, remember that not working. Dot, n cubed plus 5n plus 6 plus 3n squared plus 3n is equal to 6 times some constant, some integer. C is an integer. C is an integer. That's how it would be done. So you would mention the first one. So the n cubed plus 5n, we already said it's equal to 6 times some integer. 6 is obviously equal to 6 times an integer 1. And 3n times n plus 1 is equal to 3 times 2 times some k. Because 3 obviously is there. 2 is there. Oh, which makes it equal to 6 times. See, I forgot to write that part. And you could go ahead and explain it. Since you tell why. It's a product of two consecutive numbers, and the 3 is multiplying it as well. Therefore, in the final line, everything that we had up at the top is equal to 6 times some constant. 6 times some integer, beg pardon. And that's it. Any questions? All right, so write it off in your format. Of course, you would have to mention this part right here. I told you what to write for this, the third line in that thing, but I didn't actually write it on the board. So 3n times n plus 1 is equal to 3 times 2 times some integer, k, which is equal to 6 times an integer. And the reason is since the 3 is multiplying, and n times n plus 1 is a product of two consecutive integers. So therefore, that entire product must be divisible by 6. So you see the proofs in real analysis can be a bit more tricky, but they can be done. So sometimes it requires some out-of-the-box thinking. You could even do it by factoring, which I'll show you online. I'll just write it and show you. I'll go through it. To go through it now would take too much time. And I have a class in how much minutes? 6 minutes. So any questions? No? All right, I'll stop the recording.